So welcome to the pre-recording of lecture 5 of MCS 320 Introduction to Symbolic Computation. So today we are going to see the relationship between complex and algebraic numbers. We have seen complex numbers before many times. Complex numbers are a specific kind of algebraic numbers. So how can we see the complex numbers? Well, we start from the real numbers. We have this fancy R. And then we observe that if we look at polynomials with real coefficients, then there are some polynomials, as we can see here in this very simple example, that there are polynomials that do not have any real roots. This has all kinds of problems. We can consider any polynomial with real coefficients and divide by x squared plus 1. So if we execute a long division on this polynomial p here, then we have a quotient and a remainder. Let's forget about the quotient right now, but the remainder has degree at least has degree less than 2, strictly less than 2, because x squared, the divisor, is a quadratic polynomial. So the remainder can be defined by two real coefficients. So we denote the set of all the remainders by the division of the polynomial ring by x squared plus 1. Okay, so that's what does that bring us? Well, if you look at the remainder consists of a constant part and then a coefficient with x, r1. Now every complex number has a real part, what is here denoted as a on the slide, and then also a coefficient with the capital I, the imaginary unit. So in a leap we can identify the quotient ring, the set of all remainders, with the set of complex numbers. Why can we write all the complex numbers as a plus b times the imaginary unit? Well, the I to the power 2 simplifies to -1. In a very simple way, also that the x squared can be rewritten as -1. So there is a correspondence between the x, when we write the set of all remainders, and the set of all complex numbers. We will experiment with this. What does this buy us? Well, we can also extend other number fields. So for example, we have the field of rational numbers. That's a field that in symbolic computation we often prefer because exact arithmetic has no round off. Then it's kind of troubling that x squared minus 2 has no rational root. The square root of 2 is an irrational number. So of all the numbers, there are some that are not really rational, so they are the irrational numbers. So you can also kind of see at the picture, of course you can't really see the square root of 2 other than the intersection point of the blue curve with the horizontal axis. So but the square root of 2, the negative square root of 2, is where this parabola vanishes, but actually it never becomes 0, which is kind of unfortunate, but now it becomes positive and then negative. But kind of there is no rational number in between. Okay, so we can exactly play the same game now. So we have the set of rational numbers denoted with the fancy Q. We have a polynomial of the rational numbers that is not zero, but it's positive and negative. Then we can look at the set of all remainders after division by x squared minus 2. And we can identify this set of all remainders with two coefficients, r0, r1 here on the slide, because the degree of the remainder is strictly less than 2, because we divided by a quadratic polynomial. And we can, in very similar fashion like with the complex numbers, we can extend the rational numbers by adding the square root of 2 to the field of rational numbers. That means that now all the numbers in that extension are written as the sum of a rational numbers and a product of the square root of 2 with another rational number. So we have two coefficients, a and b, in this notation here, very similar like we have r0 and r1. So because the remainders are of degree strictly less than 2, also the numbers in this extension field are actually tuples of two elements, because the square root of 2 is 2 again. So we have now defined our first algebraic number. So it's an algebraic number because the extra symbol, so the square root of 2, is actually a symbol. That symbol is used to define the number. And we have a and b that are two rational numbers. Okay, so we are computer scientists, and the fields that actually we like are the fields of binary numbers, 0 and 2, the bits. And if you are looking at the polynomial x squared plus 1, then something funny happens. X squared plus 1 factors. So why is that? Well, if you read from right to left, then you expand. 2 times x becomes 0, because 2, when we work modulo 2, becomes 0. So you cannot use x squared plus 1 to extend the binary number field, so the field with z underscore 2 here. So because the polynomial factors. Now let's take another polynomial that is irreducible. Then, because this polynomial is irreducible, it doesn't factor, it makes sense to construct a field extension. And this field extension of a finite field, so the field z2, 0 and 1, the set of 0 and 1, with the modulo 2 arithmetic rules, then that field is extended to a field of 8 elements. So if we denote alpha as a root of x to the power 3 plus x plus 1, our irreducible polynomial, then we can simplify every power of 3 into a lower degree polynomial. In particular, alpha to the power 3 is alpha plus 1. So working with 0 and 1s has the advantage that we never have to write negatives. We never have to use the negative sign. Okay, so you could compute the size of the field as 2 to the power 3. So we have the degree of the irreducible polynomial, and we started with 2 numbers. You can also compute this very explicitly. So the set of the extended number field consists of all polynomials up to degree 2 polynomials of degree 3 can be simplified with coefficients that are bits 0 or 1. So you have two possibilities for A, two possibilities for B, which makes 4 numbers, 2 times 2, and then you have still two possibilities for C. That gives you 2 to the power 3. And you can explicitly enumerate all the elements in this field extension. And when we compute all the products of 8 by 8, we have a matrix with 64 elements, and that gives us the multiplication table. So computing in some sense is then looking up in that table. Okay, so these are the key concepts that we will illustrate in this lecture. We work with predefined complex numbers. We can extend the field of algebraic numbers, adding roots, and we can also do this with finite fields, such like the integers modulo 2. Okay, so that's the first part of this lecture. So let me now switch to the Jupyter notebook. So I have a Jupyter notebook that is prepared, so I can also eventually go to the CoCalc, but let me stick to the pre-recording. So I have a formatted prepared Jupyter notebook, which will be posted at the course website. For the remaining half hour or a little bit more, close to 35 minutes, I will work with a Jupyter notebook and rename this. So this is the 5th lecture, and this is the pre-recording. So let me make a section on complex numbers. So the two other sections will be algebraic numbers and finite field extensions. So in Sage, the field of complex numbers is predefined by the symbol CC. So kind of the fancy C, not so fancy. So I can look at a random element. So here you see a random element. The random element, as you can see, is a floating point element, because the CC works over the MPFR extended number field. We can look at the real part of Z, and I can print the imaginary part of this complex number. So you see the two components. So this can be identified with a two-dimensional plane. This is the rectangular representation of a complex number. So in the polar representation, every complex number has a radius and an argument. So let us compute the radius. That's the absolute value. So print the radius of Z. And the argument can be computed as follows. So the argument is an angle in radians between 0 and 2 pi. So you could verify the real part and the imaginary parts on any random. So here you see the random number. But looking at the radius and the angle, you just have to believe SageMath. So we can convert, so we can come back, so just to verify if this really is the argument and the radius, we can convert the polar representation into the rectangular representation by taking the cosine and sine. So I can do the converted, the rectangular version RZ, by multiplying R with the cosine, and let me do this, cosine t plus I times sine of t. And just to compare the original Z, let me line them up. And now you see that indeed I have the rectangular version and the original version. The rectangular version reconstructed from the polar representation. So I was using the I, so the I is the imaginary unit. Let me verify that over the complex numbers over C, that the polynomial x squared plus 1 factors. So how do I do this? I will have to declare a polynomial ring. So the quickest way to do this is like this. So this is a polynomial ring over the complex numbers. So in particular, the capital P is the set of all polynomials in X with coefficients that are complex. So note that SageMath, just like Python, is case sensitive. So I have the capital P for the space of all the polynomials with complex coefficients in X. And then I have the little p, which is my x squared plus 1. Now any polynomial that I write in X will automatically belong to capital P. We will make that distinction in lecture 6. So you have the general variables and symbols, and you also have the variables that are belonging to the polynomial ring. So let me verify this. So just what I said, what is P? So here you see that I couldn't really say it much better. So we have a univariate polynomial ring in X, the symbol X, over the complex field with 53 bits of precision. So an x squared plus 1 indeed factors over this field. Okay, so one last thing that I want to say, the square root over the complex numbers, the square root is a multi-valued function. So it's a root finder. So let me illustrate this. I'm going to compute the square root of -1 and ask to see all the roots. So the square root returns the capital I and the capital negative I. So it's not really correct to say that I is the square root of -1 because there are two. It's better to say that the capital I is the positive square root. Okay, so this is about complex numbers. The complex numbers are extremely useful, so that's why they are predefined. There is a kind of disconnect with Python that uses the little j for the imaginary unit. In symbolic computation and in mathematics in general, we use the capital I. Okay, so let's generalize this to algebraic numbers. So often we are reusing symbols in another context. So to reset all the variables, so I probably want to use x again. We apply the reset. So reset makes that now I can work with polynomials over the rational numbers and still use x again. So I'm going to define now, so what was the problem? So I showed it is on the slides. So one problem, so our problem is that x squared minus 2 does not factor over the complex number, over the rational numbers. So that's one algebraic way of saying it. Geometrically, x squared minus 2 has no rational roots. There's nothing much that can be done about this, but we can extend our rational numbers with the square root of 2. So how are we going to do this? Well, I will define again a polynomial ring because I want to talk about x squared minus 2. And now I'm using QQ. So P is a polynomial ring over the rational numbers. So the little p is the polynomial of interest, so the bad polynomial that has no root. So I can factor p and it doesn't factor. Now I defined p as the capital P, so the space of all polynomials in X with rational coefficients. Okay, so now comes it. So I have the extension. So I'm going to build an extension of the field Q using the symbol. I could use the symbol R, but I feel a little bit verbose, so I'm going to do the extension with the little p. So it's now a number field in my symbol. So the symbol is long spelled out the square root of 2. And the defining polynomial is x squared minus 2. So over this field, the symbol will actually simplify to, so every expression, the square of the symbol, square root of 2, simplifies to 2. Okay, so I'm now in this number field. I can now define a new polynomial ring. So remember, the analogy is that we started with real polynomials, and then we were using polynomials over the complex numbers that factored. So now I'm going to define, so now we define a polynomial ring over Q1. So I'm going to work with polynomials. Cannot use x anymore, I'm using y over q1. So this is the polynomials ring. Let me print it. Can't really say it as well that Sage does. So it's a polynomial ring in y over a number field and with square root of 2. So if now I have the polynomial y square minus 2, then that polynomial will factor. Just like the x squared plus 1 factored. Fine, what now about the polynomial y squared plus 2? So the y squared plus 2 does not factor. So similarly, so if I have the factor y squared plus 1, so that polynomial still does not factor. So any polynomial in y is a polynomial with coefficients in q1. So in order, so let me do the field extension again, I can continue. So in order for the polynomials y squared plus 1 to factor, we must build another extension. Okay, so let's do this. In the meantime, I'm saving. So how did I do this before? Well, I have to define my new polynomial ring. So now I'm running a little bit out of letters, so I'm going to use z. So I'm going to define a polynomial ring over. So I have already my polynomial over the field, so I have to define, a new extension field, q2, that will extend the field q1, and I will be very verbose, I will add an imaginary unit. So I will extend q1 with the polynomial y squared plus 2. Y squared plus 2, y squared plus 1, q2. So now I have a number field that has this imaginary unit. So let me now see that polynomials, so now I have to see that polynomials, now I can work with z. So polynomials over this extension q2 so let me use q is z squared plus 1 . Now this polynomial factors, and actually the polynomial x squared plus 2, so that's actually what I wanted to show, actually also factors. So I have added the square root of 2 and I've added the imaginary unit to it. Okay, to summarize, and this lecture actually goes very well, I prepared it well. So we work with, we start from a base field, so we started here with the field of rational numbers and a polynomial that doesn't factor. So there are two types of symbols. So there are the symbols that we use for the roots. So here the square root of 2 is the root of this polynomial that doesn't factor. So we add this to the number field. So that's what the extension is. And then we have the other symbols. So the letter x for the original polynomial field, the letter y for the polynomials in the first extension. So then we have the polynomials y squared plus 1 that do not factor. So we compute Then we select another symbol. So here I was verbose. I should not use the capital I, so that's a reserved word. But I choose the imaginary unit. So that is the name for the root of y squared plus 1. So now the polynomial z squared plus 1, after extending the number field, the rational numbers twice, first with square root of 2, then with the imaginary unit. After that, the polynomial z squared plus 2 factors. Okay, very good. So let me now come to the third and last section of this lecture, finite field extensions. I will reset everything again, so then I can use the variables x, y, z again. Also, all the definitions of the extension fields are wiped out, so I can use the same numbers again, same letters again for the symbols. Okay, so where do we start? So we start working modulo 2. We define z2 for the set of bits 0 and 1. z2 is the abbreviation for the integers 2. So a ring of integers modulo 2. So let me illustrate that the polynomial. So let me look at the polynomial ring over x squared plus 1. So you see that over this number field, the x squared plus 1 factors. So over the binary numbers, no problem with x squared plus 1. You can also verify this numerically. If you plug in 1, then 1 is a root. So 1 plus 1 modulo 2 is 0. And it's actually a double root. So when you divide x squared plus 1 using the modulo 2 arithmetic, then you get x plus 1 again as the quotient. Okay, so a polynomial that doesn't factor is x to the power 3 plus x plus 1. So this polynomial does not factor. And this is a polynomial that we can use for the root. This is the polynomial that we can use to extend the number field. So Karper is being used for fields. So I will be using alpha, or perhaps use A, it's a bit shorter. So I will extend z2 with q. So this gives me then the number field. So it's a finite field. I can ask that, so I can look at the list of all the numbers. So here you see with a simple list comprehension, I can list all the numbers in that field. So indeed we count, we have the 0 and the 1, the a plus 1, the a squared plus 1, the a squared plus a, and then the longest number has all the coefficients equal to 1. So we count 8 numbers. So we have an extension field of 8 numbers. a finite field of 8 of size 8. So you can get the 8 through enumeration, or you could also say we started with a field of size 2 and we used an irreducible polynomial of degree 3 to the power 3. Okay, so the last thing I need to show is the multiplication table. So the multiplication table lists all products of pairs of elements of K. So I do this with a for loop for all x in K. So by the way, this x is not the x that is the symbol. So you are computer scientists and you know the scope. So the x in K, the x here and also the x there, this is just a local variable. So just by lack of originality, I choose the same x for any element. So the x that is used here also in this loop is actually not the x from the symbol for the polynomials. So I'm using a list comprehension in a loop, so that's a nice way to make a double loop. So I will print all products of x by y. So x is in the outer loop, y is in the inner loop. So and this prints out very neatly all the products. So no surprise here, if you multiply with 0, everything is 0. Here you see when you multiply with 1, you have the elements of the list again. And here is when you multiply with a. So what I want to point out here is that this is a field. So every non-zero element in K has an inverse. So we can read this off from the table. So we can see that there is a 1 here and no 1 in any row and any first column or any second column here. There is exactly 1 1 in every row and every column. So you have a 1 sitting here on this, and there is a 1 sitting over here as well. So what does this 1 here mean, or what does this last 1 here mean? It means that if you multiply a square with the last element, then that will give you 1. Okay, so 1 over, let me illustrate this, what I just said, 1 over a square, you can divide so this illustrates that every non-zero element has an inverse. So all the elements that are different from 0, they form a field, as they say. So that's what all the non-zero elements, they form a group. And the entire K is with the plus and the multiplication is what they call a field. Okay, so I hope this lecture was interesting. So I prepared this lecture with a, let me scroll through my preparation. So this is what will be posted on the course website. Let me get the essence here too. So if you want to build a field extension, you first have to have an irreducible polynomial. So first you have to define what is your ring, what is your variable, and what is your coefficient field. So these are the two key definitions, key ingredients in the definition of a polynomial ring. So then when you have your polynomial ring, you have the polynomial that does not factor. That's the irreducible polynomial. And then you define the field extension. Starting from the coefficient field, you extend it with the root of the irreducible polynomial. There is another symbol that you have to pick, and that's the symbol then that denotes the root. So at first this is confusing, but if you follow these three steps, so you have two coefficients fields, the original coefficients and the extension. You have two symbols, the polynomials in the original, with the original coefficients, and then you have the symbol that you use to denote the root of the irreducible polynomial. Okay, I hope this was interesting. Let me scroll down a little bit further to see if I did not forget anything. So here in the preparation I used C instead of A, but this is fine. So it was a little bit more extensive, so I had 26 instructions in this preparation. But I thank you for your attention.